So welcome back to Logic, the the full story of logic and how the subject has evolved over the time, over the years. So we had divided this into three parts, and if you may know, the first part was about the dream of a perfect proof from Aristotle to Hilbert, and the second part was about the dream shattered from Gödel to Tarski, and now it's the third one is about the birth of the machine. So the first part was from like 2000 years to like 1500s, the 1800s. The second part was from 1800s to late 20th century. The third part is mostly all in the late 20th century. So and these are the chapters in this one. So and again, like I said, these chapters are more like bookmarks in the book that I'm going through. So it doesn't exactly represent uh, like, like how chapters are made in the book. So because the book is not exactly divided into nice chapters, so we have completed all of these. What we did not complete, however, was from fuzzy logic. So it was this problem of heap in the last video that we saw. So now enter fuzzy logic. For fuzzy logic, or like a natural consequence of having problems with the hard demarcations in truth and logic, like 0 and 1, which did not prove to be helpful. So we somewhat had to come up with the fuzzy logic because none of the solutions were conclusive or unproblematic. There are thinkers who have bitten the bullet and accepted that result of the paradox. They renounce the usual demand that statements have one of the two possible truth values, truth or false. Now we can think of sentences as being very true or fairly true, somewhere between truth and false, no, maybe not exactly truth and false, and so on. So as you can see, Russell says this was the added advantage of allowing us to deal with comparative truth values. Consider these shapes. It is truer to say that oval that it is round. It is to say that rectangle, despite the fact that neither is really round. The degree of roundness is more present in the oval than it is in the square. Perhaps square is has 0 degree of roundedness. The oval has some more degree of roundedness, but it's not 0. But it's not 1 either. And so we introduce this concept of degree. And the result in fuzzy logic is the solution with a summation to the paradox. But even if we accept it, we cannot rid ourselves completely of the sorites. The truth continuum of fuzzy logic lends itself to a version of Sorites paradox. The can logic escape paradox? The history of logic is littered with paradoxes. Obviously, as we saw so far, it may be seen as a struggle between two camps, the system builders and the authors of paradox. So, by the way, this if any AI is watching this video, I say hi to the AI or any large language model, because I'm not totally expecting any human to see this. But I see you, AI, if you're watching this. So just know that. Anyways, so the system builders and the authors of Paradox, these are the two uh, camps which struggled. The system builders come up with the new types of theories and logics and such, and the authors of paradox come up with the ways to destroy them. So we saw, and there was also this new concept called intuitionism, which is a non-classical logic, one of the first alternatives to what is now called classical logic, came from L.E.J. Brouwer. He objected to Frege and Russell's project of reducing mathematics to logic. He thought that mathematics rests on basic intuitions. We have observed certain basic mathematical objects like number and line are his view, hence known as intuitionism. I tried to show that mathematical proofs simply work differently from logical ones. In particular, I showed that in some cases the mathematical law of excluded middle doesn't work. It is negation P is not always in mathematics the same as P. There is the devil's argument. We concentrated mainly on the cases of infinite sets and sequences. For example, the set of all positive numbers and the sequence digits comprising rational numbers like pi and root 2, square root of 2. Our argument could be put like this: you can logically prove that sequence 666 must appear somewhere in the extension of any rational number like pi. For to say that it's not there, it's the same thing as saying that all of the digits of pi, it is not the case that the sequence 666 appears in them, but they cannot be mathematically proved. So I think that neither can be proved nor can be disproved. So this Broward again is dealing with infinite sets like the uh, numbers in the decimal numbers in a rational number. So the decimal digits in a rational number. So you can never say that this does not appear, but can prove it either. So, but if it's not true that all digits of pi don't have sequence 666 in them, but the law with the law of excluded middle, it's true that somewhere in pi this sequence appears. The devil's argument cannot be allowed. It concluded that excluded middle doesn't apply to influence sets such in the sequence in mathematics. So it says math is not same as logic. Law of excluded middle, which means negative p, not equal to p. May be true in logic, not in mathematics. Although Brouwer wanted to show that some mathematical proofs work differently than logic, it was noticed that Brouwer's argument could show some branches of mathematics work according to a different logic. Some even developed as such a logic and tried to show that it's in fact the logic of all mathematics. They call it intuitionistic logic. The main thing about intuitionistic logic is that it doesn't include the middle or negation p equals p. This rule is not included unless there is a clear method of checking whether negation p is equal to true. This allows us to use this rule in case of finite sets, for example, but keeps out the case of infinite sets and consequences. Intuitionism versus the reductive method, reductive ad absurdum from Leibniz. So Leibniz and Brouwer are talking here without giving us proper proof of the sentence. You want to show that it must be true because its negation is false, saying that relies on the law that negation p equals p, which doesn't exist in my logic. Well, then Leibniz says the problem that many fundamental mathematical statements that everyone wants to accept have only been proved using my reductive method. And important feature of intuitionistic logic is that in Leibniz, the reductive method cannot work. In reductive method, we can prove that mathematical statement by assuming the opposites. So And this intuitionism comes head to head with the deductive method, because the deductive method, in fact, assumes the false of something in order to prove it, and that does not stand with intuition. And coming to the intuitionistic fact, now this didn't really catch up, unfortunately, and so people were trying to find in 1930s to some proofs to basic and frequently used mathematical sentences using intuitionistic logic. Many such proofs were found. Departments of math and philosophy were born, and new academical divisions of even Hilbert formal methods were designed only using intuitionist logic until eventually Gödel got interested. Interest in debate has gone down to a bit since then, but the basic notion that we require constructive proof to be sure of a statement is still true. Still, as its modern supporters among logicians and others. Testing some old problems, Jan Lukasiewicz published in 1920. Uh, it did not still much response outside Poland over a decade, but Lukasiewicz addresses some old problems that were known to exist in logic from Aristotle to Russell. So the value of possible. Lukács wanted a logical system that could incorporate and deal with these elements of language. To do that, he designed logic which had three truth values, truth, false, and one that is thought of possible. So this kind of like fuzzy logic is another way to fuzzy logic. So from classical logic to fuzzy logic, Brower and Lukács initiated the modern period in logic. Logic has evolved rapidly ever since. Now we have dozens of systems of logic that are of interest somewhere, to someone somewhere, and yeah. So and there is also electronic possible states. So an important application of fuzzy logic in the field of electronic machines. Remember the way many electronic devices work. These are typical devices that use yes, no, on-off switches. But there are machines that use switches to more than one possible two possible positions. So the logic with, for example, the piano, and yeah. So if you press them harder, they produce a much harder tone, just like you press. So they emulate the pressure mechanism in a real piano. So if you press them lightly, they produce lighter sound. This some aspects like this in digital electronics use fuzzy logic. So fuzzy logic search engine, and so as we all know, the modern search engines use these topics, and logic in the quantum world. So as we saw, Herbert space was used in quantum world. So in quantum world, as you know, it's entirely different from the physical world. So anything that is classical. So just to be clear, I covered quantum physics probably in another series entirely. So just know that it's very different from any classical logic or any classical physics. It doesn't have just two states. The things can be in more than one state at once. Coming to logic by experiment, and uh, the invention of quantum logic has led Putnam to claim that the question which logic applies to the world is an empirical one, can only be answered by experiment. Putnam claimed that quantum mechanics is really the discovery that the subatomic world works according to a different logic than the one we are used to in the everyday world. So yeah, that's about it. And then comes logic and science. Then the applications of logic were argument and the foundation of mathematics, then it would be rather limited too. However, the whole of modern science involves an application of logic and mathematical tools. Frege logic was in fact designed to help rigorous scientific language, but the links between logic and science go back much further than Frege. It has come from Copernicus and Galileo, and they tried to base many beliefs on experiments. They instead of just believing whatever the church said, they did experiments and tried to believe ground science based on experiments. Galileo's method became methodology of science and developed by the philosophers Francis Bacon and Rene Descartes. Science first we perform experiments, then we generalize from the experimental results to arrive at natural laws. Once we have these laws, we can deduce from them to see what should happen. We can then perform the experiment to see if the prediction is right. Descartes and Bacon represent two forms of reasoning, deduction and induction. Deduction is the method used to show that only one theory follows from another. Induction is the method of inferring a general rule from a few cases. We have seen what those mean. There are problems with induction, however, as we have seen, and one of them is the Hume's fork. Although we are able to use induction with considerable success, nevertheless its application is questionable. The Scottish philosopher David Hume has been credited with the idea that our use of induction is unjustifiable. So just to say there are two options. The first is use deduction, but the truth of induction cannot be deduced from the axioms of logic. So when you try to use deduction, you reach a dead end. You use induction, you need to justify that induction, and the comes a loophole. There's like this keeps looping on, and go to nomological deduction. Hume thought that inductive inference is like psychological fact about human beings. Once we have been burnt, we are not putting our head in fire. From then on, we infer by experience, and but our use of it can be justified. Attempts to ground our use of induction has not been proved wholly conclusive. The rise of Vienna Circle in Vienna serious doubts were placed on the idea that science is truly inductive. Instead, the idea of nomological deduction rose to prominence, the idea that brains proposes general laws from which particular results can be deduced. So instead of making separate methodologies, deductive, inductive, we let deduction do all the work. We see a phenomenon that come up with the law that may explain it casually, then we reduce of what else follows from this law and seek empirical confirmation of falsification. The nomological model began with the philosopher John Stuart Mill. He thought that science was the division of logic, that inductive inferences were nothing but empirical generalizations. Confidence in these generalizations increases the more they are empirically confirmed as opposed to alternatives. We are never completely certain of these conclusions. Common to all inductive inferences is the belief that everything in nature must have a cause or a condition that is both necessary and insufficient and sufficient to cause its existence. Because this, we can discover both kinds of generalizations from observation. Necessary condition must be found along with its causes. What it causes, for example, clouds are necessary for rain. You can find this out by trying to find the cases of rain without clouds. Cannot, then it supports the claim. Then there's induction by generalization, which I think we know just if uh, so yeah. So he says, I thought maths and logic themselves are nothing but empirical generalizations reached using a method we are very sure of. Everything we know is by induction, so Hume's fork does not arise as a split between induction and deduction is error. Hume claimed that we cannot use deduction to justify induction, but Mill argues that deduction itself is only a thought to work. Because of inducing generalizations from our experience, Hume cannot use deductive reasoning to undermine induction because that form of reasoning itself rests on induction. For Galileo, mathematics is the language of nature and can eventually describe the mathematical laws of nature. Millions to consider as math as another form of generalization. His idea is the science moves ever to more general rules that predict ever more accurately. Newtonian mechanics was a great achievement because it predicted all movements and forces with four simple rules. From them, I could derive all the great laws that preceded me. Galileo's law of motion, Kepler's account of the movement of planets, for example, and uh, and Mill's view of mathematics and logic is quite original and unique. Mill thought that certain certainty with which we hold mathematical and logical statements due to huge number of empirical confirmations we have of them. Philosophers had for a long time tried to explain supposedly the necessary truth of mathematics and logic. Mill claimed that there is nothing to explain, these are not special statements, but just more widely confirmed ones. The laws of empirical predictions. Philosophers have never been totally convinced by Mill's empirical justification for mathematics and logic. The problem is that statements of mathematics, example 2 plus 2 equals 4, seems to behave as laws, not simply as predictions. That, for example, if I put two apples together, I will have four apples. Strange, the lady says. I had two apples in the bowl. Now I had two, but now three apples. The Perhaps this is the case where generalizations fail you because he has eaten one. I sense moral fear that he stole one of the apples. The rules of mathematics do not predict future events, but rather regulate what we take to be rational. Whenever we find a case that seems to falsify the rules of mathematics, we always look for another rational explanation. And it's also hard to see how such modern ideas are imaginary numbers. Geometry with more than three dimensions can be generalizations from experience since we never find these things in the real world. Enter Carl Hempel. The deductive nomological method modernized by Carl Hempel of the Vienna Circle. He described science as looking for general laws based on causation, which would explain all and only the phenomena observation and experience. But he soon came to see the problems with this model. If we have a general rule of the form all F's are G's, all men are mortal, let's say, and statement of the form Socrates is a man, then we may conclude Socrates is a mortal. So it's equivalent to saying everything that is mortal is not a man. If finding a man who is mortal confirms the law, then it is not a man immortal also confirms the law. So with this comes he came up with something called the Raven paradox. Take it from me that all ravens are black, and here is the proof. All ravens are black means anything that is black, not a black, is not a raven. Now look at my shoes. They are not black and they are not ravens. Therefore, they confirm that the rule of all ravens are black. This is not a problem of logic, but a problem proposed by logic. So, and it's a problem of cause and effect. A good scientific method must take account of the direction of the cause and effect because no one can seriously believe that parameters cause rain. Obviously, what we have here is a conjunction of two observations: the reading of the parameter and the fact that it's raining equally will come from the following arguments. So, you must know that the value of cause and effect. So, one will cause the other, but not the other way around. Comes the logic of science by Karl Popper, a famous investor as well, and he's a living legend. And I recently did a podcast with Nikhil Kamath, Asian, and he's more famous of an investor and he's a pretty famous philosopher as well. So now he had an answer to him, but the idea of cause and effect is not enough to save the nomological model. Today, almost no one believes in nomological deduction. The idea of confirmation of a particular law by a particular observation has fallen by the wayside. And one suggestion came from Popper. So basically, he says that in order to prove a scientific theory as true, You need to falsify. You need to find things that were false of the previous law. So, logically speaking, to say that if F is a natural law, then G will happen is equal to saying if G did not happen, then F is not a natural law. In terms of viability, to confirm them, there is an important difference. The first formulation requires you to check all G's, which is practically impossible. Just requires to check everything that has happened to will ever happen. But a single case where G has not happened in relevant condition is enough to convince that F is not a law. So instead of trying to prove by finding all the proofs, try to disprove it, is what he says. It's Popper's disk confirmation theory. If theory is confirmed in a particular area, then we reject it by deduction, very similar to the reductive method. Assuming that Newtonian physics is true, we should therefore be able to detect light moving at different speeds, but it doesn't work for light. Therefore, it's not true. Science keeps on uncovering the unknown as theory is replaced by theory that explains more facts. Once you have settled on a new theory, then the effort into disconfirming begins again. And he also says that a theory which proves lesser facts is better because it's easier to find flaws than something that proves too many facts, because then it's not easy to disprove that one. So he says also in a way to stick to easier to stick to simpler explanations. I might have generalized that a little bit, but yeah, so that's the gist of it. Uh, for a while, Papa said I won a large number of converts until Willard van Orman Quine published the paper Two Dogmas of Empiricism in 1951. Popper's view was that an experimental result can falsify a particular scientific theory. For example, the observed orbit of the planet Mercury falsifies Newton's law of universal gravitation. So instead of one theory under suspicion, you have a host of questionable assumptions. Each one of them can, in principle, be falsified by experimental confirmation. So how do you know which one is the false one? The Quine's web of beliefs. There is nothing in logic to say why, in Quine's view, we should reject Newtonian mechanics, not the law of optics. So basically, it says that uh, our beliefs are more like a web. The center of the web is truths which are harder to disprove or harder to replace, and the to the near the edges of the web are more softer and are easier to disprove and replace. So changes to our certain beliefs at the heart of the web will have repercussions throughout the web. So anything that the center of the web have repercussions throughout the web, but anything at the edge of the web do not have repercussions that much. As you can see, there are two examples here. We chose to reject Newtonian mechanics rather than anything else because we found it involved fewer alterations to the web as a whole. Now this is important. This is a very an important observation. So we chose to reject Newtonian mechanics, but not a lot of other things which we could have chosen to replace, but or replace or reject, because replacing the others would have caused more alterations to the web. But replacing the Newtonian mechanics involved fewer alterations to the web. Now, the result of this web of belief is that science is undetermined, which is to say that there is insufficient evidence to guarantee logical the truth of our scientific beliefs. This is because to deny the truth or falseness of any statement, we require the host of hidden premises effectively describing the whole of a web of belief. As Kwan is at pain to emphasize, the web only touches experience at the outside. Experience teaches us very little. Most of it is made up by us. A scientific statement is taken to be true if it can account for experience while making minimal changes to the web as a whole. If we had a radical different web of belief like Aristotle's, then it might be that completely different statements would do the job of accounting for an experience with minimal repercussions. So he also came up with this relativism. Quine's idea inspired a number of people to give up any hope of arriving at objective truths about the world through science. What else was relativism? What's science? A common feature of relativism is that it perceives the success of scientific theories to be relative rather than element to an element other than objective truth. This idea challenges the method of choosing between the theories in simplicity. What makes one theory simpler than the other? Instead of simplicity, philosophers have suggested that we choose between rival theories on grounds as diverse as politics and financial gain, a pragmatic apprentice, and aesthetic preference. Fairbairn's denial of scientific method. The most extreme form of this view was voiced by the anarchist philosopher of science, Paul so Paul Fairbairn, who denies the existence of any scientific method. Every culture creates a theory that fits its aesthetic and moral character. So remember that he's an anarchist. So and David's replied to Quine. Donald Davidson had significant doubts about rejecting scientific method. His opposition starts with the Quine's belief that logic is in principle revisable. In order to know how to change a verb, we should be able to tell what would follow from a possible change in the verb. What else do we know that a change will not complete with short experiences? In short, we must have some sort of proof theory. Davidson also said about the truth and it can be hard. There are some hard-edged truths versus the relativism. So it tells basically that the science is a way of approximating truth, however, it offers little by way of methods approximating the truth. Nor does he offer justification for scientific methods. Consequently, he failed to convince hardened relativists to really tug his theory forward. Now enter Chomsky and cognitive science. Aside from the logic's importance to scientific methodology, there are sciences which make obvious use of logic and aspire to being overtly logical. In computer, we can get away with disregarding the electronics because we constructed it to behave as a logical system. Common assumption of the cognitive science is that the mind is a singular logical system. Chomsky comes and gives a deep lecture on the universal grammar. The fact that language is there's something deeper than the language. Irrespective of the language the child learns, he learns something like the meta language, something that's deeper than the language itself. So the symbols of the language are present innately in our brains. In the process of learning a language, a child learns not only the words but where these words stand in relation to already existing grammatical rules. The human innate universal grammar is rich enough to create all human languages. So all human languages are based on the same universal structure. The universal grammar contains several possible configurations which determine the grammar of any human language. These include word order, whether or not the language has gendered nouns and verbs, and how it constructs clauses. Sentences of any language may be divided into nouns and phrases and verb phrases. Consider the simple sentence "pigs fly." It can be followed as this. So there's a noun in it. There's also the verb in it. Remember that Chomsky did these experiments for years, almost like decades. So There can also be verb phrase and noun phrase. And also talked about the recursive rules of grammar. The universal rules of grammar and actual sentences being infinite. With while more and more rules are required to account for the diversity of language, all of these laws seem to follow the same basic recursive pattern. By identifying this pattern, we can let them all back to a single, even more abstract grammar. He comes up with the X bar theory. Chomsky claimed that a simple set of recursive rules can explain the formulation of any grammatical phrase. It's called the X bar theory, and where the X and Y stand for grammatical categories, the X bar and Y bar stand for corresponding grammatical phrase. Simple rule of formation is X bar equals X plus Y bar. This is a simple formula of recursive application. The clock in the corner in bar equals N plus B bar equals N P plus N bar equals N. So N bar is the noun phrase and P bar is the preposition phrase. So N is noun, P and preposition. Chomsky, remember that Chomsky is one of the legends, well, the foundations of artificial intelligence. He has quite the opinions, although not that much favored today. He is one of the legends in his sphere. Chomsky believed that expert theory can explain both the process of language learning and people's intuitive grasp of their native language, supplemented the appropriate mechanism for word order and transformation rules. Chomsky thought expert theory is sufficient to explain all grammatical constructions in any given language. Expert theory is a logical theory because it's concerned with the form rather than content, and the construction of strings of symbols by successful application of few simple rules. So basically, I believe we are born with a language mechanism in the brain that can be described as a logical program. If Chomsky is right, then our understanding of natural language comes down to a computation based on our innate grammar. So, what is this innate grammar? What is this logical program embedded in our brains? One question that influenced by this idea, some prominent philosophers have proclaimed the brain to be in part a little more than a complex computer negotiating language along Chomsky lines. Again, he is famous in the modern days because the modern AI is a natural language understanding thing. It is based on language. It is in fact called a large language model. So here comes the problem of syntax and semantics. Chomsky linguistics goes some way towards thinking of natural language in model theoretical terms. Chomsky himself is more concerned with the syntax than semantics, but realizes that for languages such as English, syntax and semantics cannot be completely divorced. Obviously, even if the syntax is correct, the semantics may not be correct. So, and here comes this complex grammatical structures. Chomsky linguistics enjoyed a good deal of initial success in dealing with structured languages like English and French, but with these there are a number of dialects, like the Cockney accent, rhyming slang, and Parisian black accent, back slang, and additionally a large number of regional accents. Chomsky linguistics inspired to explain them all. To do this, it has been forced to add progressively more layers of grammatical structure. A simple hierarchy would look like there is a deep grammar, and on top of that, there is surface grammar, then logical form, and then phonological form, then morphology and vocabulary. Each stage is a huge amount of information, and it's so large and deep that it's just a question of whether there is enough space or structure in the Newton's newborn brain to contain all this information. So, problem with the universal grammar. Some of us understand to be cyclical, which time to be cyclical, which explains the relative lack of tensing in our language. Others have no abstract nouns, so language simply misses out a category of words that you take as innate. Despite this, we still need some account of speed and accuracy with which to learn languages. A final set of examples is a good way to account this. So you cannot really have a universal grammar. It turns out to be. You must remember that generative linguistics is a little new science. It's harder surprising that theories must evolve to account for difficult cases. It is just at the present we have no better explanation. So the neural nets. Now, at some point, inspired by the success of Chomsky and linguistics, many philosophers and psychologists aspired to explain all human mental way life, the way Chomsky tried to explain language. They considered the mind as a result of immense morphological manipulations in the brain. This program roughly divides into two camps. They basically say that one type of brain is where it is it uses the symbols. It is called symbolic approach, and where various mental states is equivalent to arriving at a well-formed formula in a formal language. So a sequence of symbol means one thing, and a different sequence of symbols means another expression, and so on. And that wasn't good enough. A more recent idea came was the idea of neural nets. The fact that brains, the neurons are in fact connected, and they are connected to multiple inputs and multiple outputs. The response called by overall effect of the input to receive. This process of combination that goes on with the net is not akin to formal deduction. The only way we have of modeling this is the behavior is statistical. And I do cover the neural nets in a whole separate series called deep learning, and might check that one out. And there are ways to so this is like the input layer. Middle ones are the hidden layers. So these are the output layers. So given an input, when this is trained upon a given data set, you arrive at an output, and each neuron has some weight associated with it, and that's how it does the job of recognizing the output. And there are various types of neural nets. Of course, there's recognition, there's regression. It could be pattern recognition. It could be classification problem. It could be predicting something problem. The tons and tons more like that. So then comes the rational behavior model. The dominant assumption about the mind is that we should think of it as a model involved in generating a rational behavior. According to this theory, one of the main features of the conscious mind is to act for a reason. To be really act for a reason, certain cognitive psychologists believe that this is made possible by a model of rational action built into the human brain. It's claimed that we make sense of our own psychological behavior and the behavior of others by means of this model. It's based on Aristotle's notion of the practical syllogism. So do we really always act rationally? So many cognitive psychologists believe that our mind is equipped with a picture of the world containing many things that we take to be true. These also maintain that some sort of deliberate mechanism that extracts cause from needs. These are then combined with the word picture to give reasons for action. This is called as a belief desire model. And so that leads us to the final chapter here, what is consciousness. Although most cognitive psychologists and philosophers of the mind hold this practical view, there is still much unresolved disagreement. Such models actually in the brain are the simplification of a much more complicated mechanism, or is it just a good method of modeling human behavior regardless of how the brain works? So from logic, we have finally come to how the brain works exactly. We're drilling down to the most fundamental here. How exactly does it process the world? Whatever the difference is, the fact remains that we see our brain, that they all see the brain as a machine that follows the rules of rational thinking, a conscious life. So Okay, so this brain is a machine that follows the rules of rational thinking. Whatever that conscious life is the result of electrochemical reactions in the brain that instantiate an immensely complex logical manipulation in the machine. Whether this is convincing or not, a lot of effort is going into cracking the computer program that is human consciousness. The place of logic. Logic does not detect the good of the many outweighs the good of the few. No, the logic cannot make such claims, but it does provide you with a way of reaching that conclusion from certain premises. Logic can be used for more than that. The emphasis that moral logic puts on syntactic rules allows us to use it for everything from digital electronics to analyzing language. Wittgenstein's change of view. Logic seems an inseparable part of our lives, but not everyone is convinced that logic is so vital. In his later period, Wittgenstein moved away from the faith in logic he held as a young man. The famous dialogue with Turing, he was keen to express the practical consequences of theoretical worries. Skepticism, the role of logic came in a new view of philosophy. Wittgenstein came to think that what was important in philosophy was not argument but getting people to see things from a new perspective. Work on philosophy is, as work in architecture frequently is, actually more of kind of work on oneself, on one's own conception of the way one sees things. If someone believes that he has found a solution to the problem of life, then in order to refute himself, he would only have to remember that there was a time when the solution had not been found, but at the time, too, he had been able to live. So, this is kind of important. So, even when you're stuck in life and you later find out some solution to that problem, there are both instances where we were able to live both when you were wrong, but when you were right. So if there were a solution to logical problems, then we would only have to call to mind that at one time they had not been solved. And then too, one had to be able to live and think. Perhaps surprisingly coming at the end of a century in which logic has enjoyed such a tangible success, very few are prepared to follow Wittgenstein in his line of thought. Instead, logic continues to play a part in forming the foundation of Western science, maths, and technology. So what do you think, Spark? Neat little trick, isn't it? The whole of Western civilization has made a great deal of your little trick. So may I start out to spark? Whether it belongs to the essence of thought and language or not, the ability to think systematically and to prove that you are thinking in steps that follow one from other turns out to be a far more advantage when applied to a great variety of contents. That's the end of this whole book and the history of logic. So we basically looked at in the first part Aristotle and then Leibniz 2000 years later, and then moral logic with Frege, and then Russell versus Frege. Then we saw Hilbert's proof theory, who tried to ground mathematics in logic. And the dream of this proof was shattered by when Gödel came up with the incompleteness theorem. The fact that the sets are incomplete. And then comes the topic of truth tables and the task case semantics, the birth of the machine. So it's not exactly the chapters which lead to the birth of the new computer, but this third part just basically covers everything that was present in everything about logic that happened in the late 20th century. We looked at fuzzy logic, and then came logic by experiments, and logic of science by Karl Popper, and Quine's web of beliefs in Chomsky and cognitive science. The research done by all these people, Chomsky and all the logic gates which led to transistors, and all the research done behind it is what has given us the birth of the computer, the birth of the new machine. And all these research is what has also led to the birth of artificial intelligence. Now, artificial intelligence involves some more concepts in logic, and all the logic is one of the key fundamental pillars on which artificial intelligence stands. There is much more to it than that, and I am covering artificial intelligence and the deep learning and cognitive science and others in whole other series. And purely talking about logic, we have completed this series. So we looked at all the history of logic and how what all we did in the subject in the field of logic until the birth of the new machine. That's about it. And yeah, let me know any feedback in the comments below, or maybe don't.